Welcome to your Chapter 7 Encryption and Cybersecurity Review. We're going to go over MCs 28, 29, 30, 31, and 32. I'm going to go through all the questions, try to go through them relatively quickly for you guys, but get you the information that you also need. Looking at MC number 28, question number 1. A couple of people got this one wrong, and I think they had the right intentions. But the idea was that you are trying to send a message to someone online. You are going to use their public key to encrypt the message. And the question became, what does that person use to decrypt the message? When you encrypt a message with somebody's public key, they are the only ones that can read that and decrypt it with their own private key. I think a few people saw the word private key, but notice this one said that it's the sender's private key. It's the recipient, the person who we are encrypting it with their public key. They are also going to use their private key to decrypt that as well. Number 2 talks about symmetric encryption. And remember, symmetric is when we use the same key to encrypt a message and to decrypt the message. This is very commonly used in the Caesar cipher algorithm, which is what letter B is basically describing, where Finn and Gwen use the same key. Finn uses it to encrypt the message. Gwen uses it to decrypt the message. They would both have to adjust the letters 5 times, for example, forwards, and then 5 times backwards as well. Symmetric, you want to think of the word same. What about public key encryption? Public key encryption is the exact same thing as asymmetric encryption. We call it public key because we have a set of public keys and private keys, and we use them interchangeably together to send and receive messages. This one, again, is a nice way of doing this with strangers online. And I don't mean strangers, but websites that don't necessarily know who we are or where we are in the world. We can safely send that information by utilizing that website's public key, encrypting some information and sending it to that website so that they can then verify that information is being sent encrypted and that nobody has intercepted and changed their messages whatsoever. So it leaves us out of the hand of eavesdroppers. This next one talks about transmitting your private data, and specifically it says you're trying to send something, in this case sensitive, to another user. How would you do this with the world that we live in? And I look at this and I say, well, man, you could use symmetric or asymmetric. Either one of those is a possibility. They didn't give you a scenario set up. But if you look at this, the only one that they have encryption-wise is actually the public key encryption. Creative Commons licenses, I think some people might have got that confused with digital certificates. This is not something that verifies, or it verifies websites, but it doesn't mean that our information is safe on those websites. Bandwidth has no connection with encryption whatsoever, and either does routing. You would hope that the information is being encrypted prior to leaving your computer or your device, and that is why public key encryption is the answer that makes the most sense in that scenario. Lastly, a little bit more about symmetric encryption and some of the details about it. Symmetric encryption, you do have that one single key. You want to make sure that that is kept private and only you and the recipient of the information you're trying to send back and forth, you guys are the only ones who know what that key is. If that ever does get out and about, unfortunately, you will need to create a new key. Looking at MC number 29. We love digital certificates online. This is the one that verifies websites for you. When you get an IP address, we go to these digital certificate authorities and we double check and say, is this the IP address that you have online? Does your certificate match mine? In the situation that we use these for, digital certificates are not actual physical certificates, but rather they're talking about the encrypted keys that we use. So these digital certificates, in a sense, are kind of like a set of public keys from websites, and we gain a public key from somebody. We just verify, is this the public key that you have on file? A little bit easier to talk about them as digital certificates. When it comes to being fault tolerant, that has nothing to do with digital certificates, unfortunately. That is a situation where we try to have a quote-unquote backup plan in case part of the internet shuts down or breaks. The rest of the internet is still capable of running and making all those connections. Multi-factor authentication, this is that step where you try to log into a computer and they say, wait a second, I just texted you a second code. Can you verify that that code is what it's appropriately supposed to be? So you actually are using a trusted device in this situation to have an added layer of security to your logins. And with this, we talk about which of the following is not an example. The idea of this is, and if you read this one, it says, if you misfire on your password twice, can I lock you out? That is not two-factor authentication. When we need two-factor authentication to work, we need to make sure that we are receiving a second notification to a device that is trusted to us. That helps us verify that we are the owners of the account on hand. That's the big key takeaway. This one deals with key logging. Remember, key logging can be a physical device. It can be a software that registers and tracks the keystrokes of a particular keyboard or computer. And in this scenario, they're talking about how it can possibly be used to gain access to computers. And I ran through this scenario with you guys earlier where I said we had a student who had downloaded this software, and you can see when somebody types in www.infinitecampus.com. You're registering every keystroke. Once they go to that website, the first thing they're likely to type in is going to be their username. The second thing that they type in is very likely going to be their password. If you have these keystrokes, you are able to, in a sense, analyze those and determine which of those keystrokes were meant for the password, which of those were meant for the login information. That's another way of accessing somebody's information or even bank account information without them really knowing. A very sly way of doing it. Question 4 of this discusses more so the idea of weak passwords and how they're not good. There's a reason you want your passwords to be strong. There is such thing as called brute force attacks. Brute force attacks are when we try every possibility out there to see if any of them will work. And usually the simpler your password is, the more susceptible it is to a brute force attack. Not saying that it's guaranteed to work, but if your password is only 4 characters long compared to a password that is 12 characters long, there's a lot more work that has to go into that 12-character password. So by making these very strong passwords, you are keeping yourself safer online. Question 5, talking about privacy risks. This is a very common thing we see these days with facial recognition and how much information is being collected without us knowing. In this example, a police department is collecting license plate information of cars that are driving and parking throughout the city. The question is, where are they keeping this information? What are they doing with this information? How could it possibly be misused? And the number one stick away that we have here is, wow, this information, we could track residents if we see their vehicles being driven on this street or this street. And connecting some dots together, you could potentially find some daily activities for a person, which could make them susceptible to stalking or anything of that situation that we're really trying to avoid at all costs. MC30. I'm going to fly through these. I only have a 15-minute time limit for this, so I'm going to see if I can squeeze these all in relatively quickly. Which of the following is a drawback of symmetric key encryption? This is the one where the drawback of symmetric key encryption is that you have to have a shared secret. If I go to ESPN.com, I have to send a piece of information over the internet first to verify a connection. That first message back and forth, if I'm trying to share the secret key, that could be an issue. You would have to make sure that you are using asymmetric first, utilizing ESPN's public key to help you out there. Part two, I think this is important to understand the order in which these happen. If you're trying to send a secure message, the first thing that has to happen is you have to generate a public and a private key combination. This is like our activity today. Once somebody has a public key, they can make that public key available to anybody. So the first thing that has to happen, we're generating those public and private keys. Next up, we're going to use which one is this? It looks like we're going to use the public key to encrypt what we want the shared secret to be. So the very first message is saying, this is our shared secret. After that, we are going to then encrypt messages back and forth using our shared secret key, which is the whole bread and butter of these TLS handshakes that we talk about. Let's see. Oh, this is a good one with sensitive information. I want to look at these examples and talk about why some of them are good or not. So we're again trying to protect our information. Should we store passwords and usernames on an online database? No, you should probably be storing hashes of those so that we can't recreate your passwords from those. Should we send emails with credit card information? Please don't ever do that. Never send your credit card information unless it is a verified, valid website. Should we allow people to choose to use HTTP? Probably not. That is very susceptible to plain text being sent, which means, again, if you send credit card information, somebody has that. But instead, we should probably make sure that all of our information is encrypted using HTTPS for those examples. Next up, compromising users' personal privacy. Which of the following has the least potential for this? What if you use the same passwords over and over? If somebody gains your password for one website, they now have that password for all the other websites as well. Probably not the best scenario for you guys. Should we communicate in plain text? No, we should probably make sure we are encrypting all of our messages. And this is a big one that people forget about. When you set up your Wi-Fi at home, are you using the default administrator password? There are websites out there with lists of thousands of default passwords. You could potentially be susceptible to somebody infiltrating your router's information and then therefore potentially stealing your information as well. Instead, is it safe to post your public key for everybody to see? Absolutely. You need to post that public key in order to make everyone accessible to your website. And last but not least, I'll go finish this one off and then I'll have to start a second video for you. Which of the following is false regarding the key size that we use these days? Remember that larger keys means that users are going to have, or I should say, malicious actors are going to have a more difficult time trying to break into your system. So some of the things you want to point out, every bit that I add, so in this example I went from 256 to 257 bits. What that means is that there are now twice as many possibilities. So it's exponential growth. Adding a single bit adds twice as many possibilities every time. What about the law that we have that says every approximately 18 months, Moore's law, the speed of computers doubles? Well, guess what? Every 18 months, that means that extra bit that you added, they can now compensate for that and potentially get that. So we now, every 2 years approximately, need to make sure that our encryption practices are still strong relative to what the standards are for computers. The one that we really wanted to look at, every time you make your key longer, it's definitely harder to get into. And again, that's called that exponential growth, where every instance you're adding, it's a multiple factor of how many possibilities there are to crack down on that. I will be going through the last two MCs, 31 and 32, in a second video. Watch out for that one.